Hey guys, you want to cover everything you need to know about energy for springs on the MCAT in 5 minutes or less? Let's get that done right now. Let's review that one more time before we get to the heart of this stuff, which is really energy. Okay? So here, Hooke's law says you got to account for the springs. Some springs are really strong, others are not. I get that. That's represented by this constant. Okay? All right. So this negative, all that tells us if you pull one way or push one way, it's going to push back in the opposite direction or pull back in the opposite direction. Okay. And this displacement here tells you the farther you stretch it, for example, or the more you compress it, the harder it's going to push or pull back. Okay. I get it. So this thing is done. The key to the improbable springs is energy. So we need to look at the energy version. Okay. Remember in general, there's energy because you're moving, right? That's kinetic energy. And there's energy due to your position. That's going to be potential energy. Okay, so I'm going to start writing this as kinetic energy and potential. It's a notation I'm going to use. Okay? And conservation energy works beautifully for springs. First, let's set this up. I have my spring at equilibrium, right? I take it and I stretch it, so now it's here. Okay? So set up as I have the spring, I have it here, I let it go. Okay? It's going to go back over to equilibrium, push past equilibrium, get maximally compressed, and it's going to go back to equilibrium. Hopefully this picture isn't confusing. So what I'm saying is, this is your happy point equilibrium. We stretch it out to some amount, we let it go. It's going to be flying back to equilibrium, but when it gets to equilibrium, it's already moving, so it's going to keep moving this way. Now you're compressing the spring, so the spring is going to push back. Now keep pushing until maximum compression, then it'll come to a stop, right? Where the spring is going to push really hard and send it back to equilibrium. And if there's no friction, you're going to be bouncing around like this pretty much forever. Okay? All right. So let's talk about this. When you're at maximum stretch, right? The second I let you go, you're not moving. So the kinetic energy here is zero, right? Because we just let you go. However, because of your position, you're not at equilibrium, the spring is going to pull back on you. So that's a lot of potential energy. You're going to have maximum potential energy because conservation energy, the total energy is potential plus kinetic. Because of your position, you have energy, but you're not moving at all. So all of your energy must be potential. Okay. Now, as we start to pull like this and bring you back, you still have potential energy, but now you're moving, so you have kinetic. What happens though when you get to equilibrium? When you get to equilibrium, now the position gives you nothing. The second you're here, the spring is happy, right? But you're hauling butt because we pulled you along, you're moving super fast. So now all of your energy is kinetic. Okay? But none of your energy is potential. All right. Now, because you're moving, you have kinetic energy, you keep moving. And now the spring's pushing back against you. When you come to a stop here, you're not moving, so the kinetic energy is zero. But the potential energy, that's maximum. It's conservation energy, right? You had a certain amount of energy. It was all because of your position, potential. Now you go to here, the position gives you nothing because the spring is happy. So it's all kinetic. Then we convert that kinetic back to potential. Here you come to a complete stop. So no kinetic energy, all potential. Okay? So what's really happening here is you're doing this dance between potential, kinetic, potential, kinetic, potential, kinetic, etc. Okay? One thing that the students get really confused about, so I want to be clear on this, is the acceleration. So first, quick observation. When is your speed the greatest? Well, kinetic energy is 1/2 mv squared. And what that means really is the faster you're moving, the more kinetic energy you have. So your maximal kinetic energy is here, but this is also where your speed is maximal. However, that's not necessarily where the acceleration is maximal. So even though you're hauling butt, you're going super fast here, right? The second you're here, nothing happens. The spring is happy. It's not pulling you, it's not pulling you, pushing you. So your velocity, whatever it is, right, it's not changing. So the second you're there, the spring is not messing with you. So believe it or not, the acceleration here is zero. Remember, the acceleration is your change in velocity, okay? And velocity, in this case, we can think of as your speed plus the direction you're going, okay? Over on this end you have to imagine you are perfectly still. Now we're going to make you move. That's a big change from still to moving, right? So I think intuitively, this would be max acceleration. Same thing here. You're still and you're about to move. So here again, max acceleration. We could definitely geek this out and make this clear. Okay? So you remember you have F equals ma. So the greater the force, the greater the acceleration. But we know from Hooke's law, the greater the displacement, the greater the force, right? You're pulling really hard when you're far away from equilibrium. So if the force is maximum, F equal to ma, and mass is the same, then the acceleration must be maximum. When you're here, the displacement from equilibrium is 0. So according to Hooke's law, so remember Hooke's law is negative ks. If the displacement is 0, the force is 0. And if the force is 0, the acceleration is 0. Same thing over here though. When you displace this amount, right, you'll have a big value over here. Don't worry about the sign, we're just worrying about the magnitude. So this force will be greatest in magnitude. It'll be the greatest in magnitude even if it has a negative sign. So it'll be super big over here, which means the acceleration will be greatest, okay? Again, maybe I should be clear on that. When we say max acceleration, we mean in terms of magnitude. So one of these accelerations, like this one, will actually have a negative sign. This acceleration will have a positive sign. So technically, this guy is bigger than that in terms of raw numbers. This might be like negative 20, and this is plus 20. So when I say max acceleration, I really mean the size of the acceleration, the magnitude, not accounting for the direction of the sign. So hopefully that helped. That is basically everything you need to know about springs in terms of Hooke's law and energy. There is this idea of using a cosine wave to represent this stuff, but that's a different issue. So we can talk about that later if you want. If you have any questions, let us know. If you want more MCAT problem solving help, check out our new Physics MCAT problem solving book, where we lay out the problems, let you have a try at them, and then give you the solutions with the major themes along the side. You can also check out our mini course that goes along with that, our workshops, or if you're interested, the full MCAT course. If you have any questions, let us know.